Julian Barbour, The Janus Point, A New Theory of Time. Venture into the intriguing realm of time and its mysteries with Julian Barbour's The Janus Point, A New Theory of Time. This book questions the conventional understanding of time's direction and offers a game-changing theory that will have you questioning everything you know about the natural laws governing the universe. Explore the Janus Point concept and its implications on the past, present, and future. Delve into the exciting ideas around time reversal symmetry, entropy, and the increasing complexity of the universe. Immerse yourself in thought-provoking discussions on the microscopic level of natural laws and tantalizing theories about the beginnings and ends of our universe.
The arrows of time. Time, as we know it, seems to flow in a single direction, and we feel its impact with each passing moment. While this notion is ingrained in our day-to-day lives, the laws of nature do not differentiate between the past and future. The concept of time is fascinating and perplexing. It is often believed that our understanding of time's direction stems from the increase in entropy, as stated by the second law of thermodynamics. However, the author challenges this explanation and suggests another explanation behind the arrows of time. The microscopic level laws of nature are a mirror image of each other when in reverse, and the distinction comes from our macroscopic and familiar world. Janus Point Theory. The Janus Point theory challenges the notion that the Big Bang was the birth of time. The author proposes that time may have split off into two directions after the Big Bang. If this is correct, the direction of time we experience is dictated by which side of the Janus Point we're on. The theory is named after the two-faced Roman god and imposes no special conditions whatsoever. It argues that the laws of the universe lead to a Janus Point, a condition where the size of the universe either becomes zero or passes through a minimal value. The Janus Point theory also implies that the growth of the universe is not ruled by entropy but by complexity, a measure of structure or order. The universe's complexity. The widely accepted theory of the end of the universe is heat-death. However, the author contests that the universe may be increasing in complexity instead of entropy. The author argues that complexity contrasts with entropy, and complex subsystems like Earth appear as byproducts of the universe's growth in complexity. Entropy, which relates to thermodynamics and the steam engine, does not equate to the universe's structure as it is constantly expanding. Thus, evidence of complexity surrounds us, from billions of stars creating new elements to the multilayered strata of rocks beneath us, and continuously expanding towns and cities. The Janus Point model and the three-body problem. The Janus Point model is explained with the concept of the three-body problem, which asks us to imagine the entire universe as three particles. The singleton, unpaired particle, approached the Kepler pair, and the resulting motion became chaotic. After passing the Janus Point, the system returned to the singleton and a Kepler pair, and the laws of time reversal symmetry were preserved. This means that space as well as time is affected, leading to a perfect preservation of the laws of time reversal symmetry. Understanding Entaxy, bringing order to the universe. The Janus Point theory introduces the concept of entaxy to explain the decrease of microstate counts within certain macrostates in the universe. As particles are released from their box at the Janus Point, they move in a highly structured manner that contradicts the increase of entropy. Entaxy describes the count of all possible microstates within a macrostate, which decreases as particles cluster together to form complex subsystems such as stars, galaxies, and black holes. Even in the three-body model, entaxy holds up as particles move away from each other in a clock-like manner. Entaxy brings a new understanding of order in the universe and challenges conventional entropy. The Janus Point and the emergence of structure. The universe is made up of particles that come together to form shapes, and these shapes coalesce into subsystems of ever greater complexity and order. But how does structure emerge from chaos, and what happens at the Janus Point, the moment of total collision? The Janus Point occurs when a universe's size approaches zero, and two sets of rules govern what happens here. In Newtonian mechanics, the universe size goes to zero, and gravitational forces direct each particle to the exact center of mass, followed by a total collision, resulting in the Big Bang. In general relativity, the universe behaves chaotically as it approaches zero size, making it impossible to reach the Janus point. One theory proposes a solution that requires a massless scalar field, a type of matter thought to have been present at the Big Bang. This theory suggests that the shape of the universe eventually reaches size zero, emerges on the other side of the Janus point, and explains the arrows of time. Although this theory remains unproven, it is at the forefront of scientific research.
In conclusion, the Janus Point, a new theory of time, challenges our preconceived ideas about the nature of time, its direction, and the laws governing the universe. Julian Barbour presents an alternative explanation, suggesting that the Big Bang may have been merely a very special location in time rather than the true beginning. By exploring the concepts of complexity and entaxy, he proposes that time may have split off into two directions after the Big Bang, depending on which side of the Janus Point we're situated. This groundbreaking theory has the potential to revolutionize our understanding of time and the universe as a whole. And though it may remain unproven for now, it opens up fascinating new pathways for scientific inquiry and our perception of reality.